All right, so I know I mentioned this once before, but on Thursday, we introduced our trigonometric ratios, sine, cosine, and tangent. We dropped them into equations. We're going to use those again today, but we're also going to look at how we can make them not technically disappear, but how we would do the opposite of them. And the idea behind this is being able to continue to solve equations where trigonometry is involved, but we're going to rely on the same processes we used when solving other equations. So for example, when we were trying to get a variable by itself, and it was like x plus 3, we did the opposite. We subtracted 3 from both sides. If it was like 2 times x, we did the opposite. We divided both sides by 2. Anytime we were solving an equation and we wanted something to disappear from one side, we would just do the exact opposite of what was being done, making sure to do it on both sides. What that allowed us to do then was eventually whittle it down to get what we wanted by itself. So there are inverses for our trig ratios, which we're going to use today. They look a little bit weird, but our calculator is going to help us some more. So we're going to jump right into it. If you have your notes from Thursday, those might be handy to have nearby in case you have forgotten. If you don't have them nearby, up here in the top right margin, I'm going to do that little, I think it's called a mnemonic. So, Toa was the little trick that we used to be able to remember which ratio went with each. So sine was opposite leg over hypotenuse, cosine adjacent leg over hypotenuse, tangent opposite leg over adjacent leg. That was in our notes from Thursday. Again, obviously, so was a bunch of other stuff, but that's going to help us maybe set up our equations for us today. So as it says there, if you know the sine, cosine, or tangent of an angle, you can actually use what's known as the inverse function of that trig function in order to undo it or go away. So what I'm going to show you here, I'm going to highlight it first. So the inverse function, the way that you visually can identify that you're dealing with an inverse is the little -1 exponent that is attached to it. And we're not going to treat it like an exponent. We're going to say that this is an inverse function. Those of you who did the assignment on Thursday, if you look at your calculator that you used, typically when you press the second button and then press, for example, sine, it's going to do the inverse sine. Second cosine will do the inverse cosine, same for tangent as well. So we're going to practice this out here. We're going to set up some relationships. We're going to go through it, see what we can do. We want to try to be as detailed as possible so we can trace our steps and hopefully not lose anything. So we're going to jump right into it. My first recommendation, always use either the angle you know or the angle you're looking for as your focal point. So it just so happens that the X that we're looking for is the angle measurement. And with respect to that angle, what size of the triangle do we know? Hypotenuse. We know the hypotenuse. That's going to be our 24. It's always opposite the right angle. And with respect to our angle that we're looking at, 15, is that opposite or adjacent leg? Opposite. That is the opposite leg. So which trig function uses opposite and hypotenuse? Sin or sine. Absolutely. So what I can do here then is I can say that the sine, give myself a little bit of extra space here, the sine of our angle, which is x degrees, equals the ratio opposite leg, which is 15, over the hypotenuse, which is 24. Now, What's different from Thursday is that, unlike Thursday, our variable isn't trapped in the ratio, it's trapped in our trig function. The way we can get rid of this is by doing the inverse of sine, but we have to do it to both sides. Here's what that looks like. This extra step is going to seem a bit messy at first until we clean it up. So I'm going to, let me put my little boundary line in here. I'm going to take the inverse sine, which is denoted with a little exponent of -1. Oh no. Of the left-hand side, which is the sine of x. But whatever we do to one side, we have to match it on the opposite side. So I'm also going to take the inverse sine of 15 over 24. Now on the left, it looks like a hot mess, but what we're left with is that the sine, the inverse sine and the sine, because they are inverses, undo each other, leaving me with just x. On the right-hand side, this is going to be where we're going to need our calculator to be able to actually calculate this. Now, depending on your type of calculator, it may accept a fraction. Some calculators will do its fraction with a division sign, but if that is the case, make sure, because usually when you do an inverse sign in your calculator, make sure you close the parentheses so that it knows it is taking the inverse sign of this whole ratio here, 15 over 20. Sorry?
38.7.
38.7. And because it is an angle, I'm going to put the little degree symbol on it as well. Now, if you're a bit hesitant on the fact that you're using a fraction inside this new function here, you can, if you need to, find a decimal approximation of 15 over 24. To do that, you would just take 15 divided by 24 and then take the inverse sign of that. If you have a scientific calculator, though, it should be able to do all of this. Now I'm going to pause for just a moment because I know Misty got it. I want to make sure that everyone else, depending on the calculator you're using, you could take the inverse sine of 15/24 and get this value here. So Misty, you're good. Shanitha, you're good. Logan's nodding. Jonathan, you usually use a phone calculator, so I would play around with that at some point today to see if you can get it as well. And the reason why I say that is because on Thursday we mentioned how it's important that our calculator is in degree mode, which is usually the default. But depending on the calculator, if it were switched to what's called radians, it's going to give you a different value here. So I just want to make sure we're on the right track here together. But otherwise, in a nutshell, that's an inverse trig function. So we're going to try all 6 of these here at the top, because then after that, we're going to do a little bit of review from Thursday, and then we're going to introduce a handful of word problems. Uses the same skills here, but then it's going to require me to embarrass myself with a little sketch or a diagram to try to draw based off of the story. So number 2, same idea here. Again, use that angle as your focal point. That's where our x that we're looking for is anyways. With respect to that angle, what sides of the triangle do we have?
Sine.
Sorry?
Sine.
Careful, before we jump to the trig ratio, tell me which sides you're seeing there. What would,
The hypotenuse.
hypotenuse would be one of them. That would be the 11. What about the 8? The opposite or adjacent?
Opposite.
Careful. If it's touching, or if it's one of the sides that make up that angle, it wouldn't be opposite.
No, it's adjusting.
It would be the adjacent one. So that is going to change. It's not going to be sine this time.
It's cos.
It's going to be cosine. So I set it up. Cosine of the angle, which is x degrees, equals the ratio of cosine, which is the adjacent leg, in this case 8, over the hypotenuse, which is 11. Same goal, just trying to get x by itself. It is trapped inside of the cosine, so we do the opposite of cosine. That is the inverse cosine. So inverse cosine of the entire left-hand side. That means I also have to do the inverse cosine of the entire right-hand side. On the left, nothing too exciting there, except for the fact that the inverse cosine and the regular cosine eliminate each other, leaving me with x. On the right-hand side, then, this is going to be where we say, okay, calculator, help me out. I need to know the inverse cosine of 8/11. 43.3. Anyone else second that? Got a couple head nods there. Sounds good to me.
Hey, can you walk through just like typing that into the calculator again?
Typing this into the calculator. So do you have a scientific calculator or is it on your phone?
I'm using it on my phone.
Okay, so there may be two ways to do this. My first guess on a phone calculator is you're going to have to actually start backwards. Try doing 8 divided by 11.
I figured out how to do it on mine.
Is yours backwards as well? Do you have to do the fraction first?
No, there's a little button.
That changes it for
Yeah,
you?
that changes it.
Okay.
Do you see like a button that has 2 arrows pointing in opposite directions?
Do you, oh, Tira's shaking her head, yes.
Yeah.
He says he pressed that button and did it change it to the inverses for you?
It changed everything to inverses.
Yes, thank you.
Awesome. Tara, if you want to try that out real quick, see if you get 43.3 for this one. And then that way, Jonathan, did you get that value as well? Did yours work out? So we'll,
43 point, yeah, I got it.
okay, good. Which I'm assuming there's some rounding going on here, which isn't too much we're going to spend time on. Tara, are you good as well? Awesome. Good. So it's really good exercise to get comfortable with whichever calculator you're using, because every one of them is a little bit different. I think most of them, normally you do the inverse trig function first, followed by the fraction. But I have seen some where you actually have to do the fraction first and then take the inverse trig function of that. So being familiar with your calculator is a must. Number 3, same idea. Our angle is our focal point, which also happens to be where our variable's at. With respect to that angle, what sides of the triangle do we have? Do I have the hypotenuse again?
No.
Not this time. So that means one of them's opposite leg, one of them's adjacent. Which one's opposite? So we're going to use tangent, but in our diagram here, which leg is opposite?
20.
The 20. Helps to label, in my opinion, just so we don't accidentally scramble them up. So opposite leg is 20, adjacent leg is 37. Missy already said we're going to use tangent here. That is the ratio for opposite and adjacent. I'm going to set it up. Tangent of my angle equals the opposite leg, which is 20, over the adjacent leg, which is 37. And you're going to notice it feels fairly repetitive. The one thing that you might accidentally mess up is if you accidentally use the wrong trig function. That's really going to be probably the most common mistake. But if I went through here, I need that tangent to get off of that x, so I'm going to use the inverse tangent. Which means I'm taking the inverse tangent of the opposite side as well. On the left, tangent and inverse tangent eliminate, leaving me with x equals the inverse tangent of 20 over 37, which my calculator says I can handle that. 28.3. Double check for me.
28.4.
I think it rounds up 28.4. Now, at the end of the day, when we test over this, if you miss round and you're off by 1/10 of a degree, I'm still going to give you full credit. You did the majority of the work. I'm not here to grade you on how perfectly you can round. Now, if you do something that's way off the mark, then I'm going to maybe knock off partial credit. But if you're just off by 1/10 because of your rounding, I'm going to credit that back to you. Yeah, like I said, these are going to feel a little bit repetitive. The only thing that's really changing so far is which trig function we're using. So on number 4,
I had a quick question, Josh.
go for it, Tiara.
Sorry. Okay, so is it negative because we're working with this angle on the inside, correct? Is that why it keeps being like we're
The
using that?
little -1 on it.
Yeah.
So yes, in this case, our variable, what we're looking for is a missing angle measurement, which means when we set up that relationship, we can take sine, cosine, and tangent of an angle. We don't know the angle this time, so we actually need to undo that relationship, peel it away. And just like we solve any other equation, it always comes down to doing the inverse. The inverse of addition is subtraction. Inverse of multiplication is division. The inverse of the square root is squaring something. All operations and functions have an inverse. We can then use it to make things disappear. That's a good question. So taking a look at this next one here, using that angle as my focal point, which sides of the triangle do we have?
Hypotenuse,
We have the hypotenuse at 23. And which leg do we have?
the opposite.
Ooh, is it touching the angle?
I'm sorry, yes, it is.
So it's adjacent. That might be a good one for you, Misty, to use, is ask yourself, is that leg touching the angle? Because if it is, then it's most likely adjacent. So adjacent and hypotenuse tells me which trig function?
Cosine.
Cosine. So we're going to take cosine of our angle, which is x degrees, equals the ratio of the adjacent leg, 18, over the hypotenuse, which is 23. So I'm going to do the opposite or the inverse cosine on both sides. It's going to help me get that x by itself. On the left, that eliminates, leaving me with x equals the inverse cosine of 18 over 23.
38.5.
38.5. With the help of my calculator, it can take that inverse cosine rather quickly. Takes out the guesswork for me. Moving over to number 5. Again, the reason why we're doing all 6 of these is just because it's a little snippet of inverse operations. Because the next section, we're going to do a little bit of review, and then we're going to transition into some word problems. So number 5, again, using that angle as my focal point, what sides of the triangle do I have?
Hypotenuse.
Hypotenuse there at 41,
And then opposite.
and I have the opposite leg there at 40.
Mm.
So we're going to use the sine of our angle. So sine of x degrees equals our ratio, opposite over hypotenuse, 40 over 41. And do the inverse sine of both sides. Knocks it out on the left-hand side, leaving me with just x equals the inverse sine of 40 over 41. Go to my calculator.
73.3, 77.3.
77.3. Good. So if you haven't noticed yet, the setup is very important because it will drastically affect which inverse you end up using based off of which trig ratio you have enough information for. So setup is crucial. Hop over here to number 6. So again, using this as my focal point, the angle again, which sides of the triangle do I have?
Adjusting
The adjacent there
Adjacent, yeah.
at the 5, okay,
and then opposite,
and the opposite leg as well.
which is the tangent.
Yep, we're going to use tangent here because we don't know the hypotenuse. So tangent of x degrees equals opposite over adjacent. So 7 over 5. I'm going to take the inverse tangent of both sides. So after the tangent and inverse tangent eliminate on the left, I am at x equals the inverse tangent of 7 over 5.
54.5.
And with the calculator, we should get 54.5 degrees. What do you guys think? Not too bad. So initially it's scary because all of a sudden we're throwing these then like abbreviated words in the middle of an equation. But as long as you know that it behaves like any other operation, addition, subtraction, square rooting, radicals, things like that, and you know that you can make them go away by simply using its inverse, then we're not dead in the water. We can work our way through these. Now, see if I can fit them all up there. That, again, was a very brisk, but fairly varied set of practice examples in which we needed to use the inverse sine, cosine, or tangent. Now, to help build us up to our word problems for today, we are going to practice a little bit of our OG sine, cosine, tangents from Thursday. And some of this review may help you if you're still stuck on the assignment from Thursday. And I'm not going to do every single one. I'm going to cherry pick a few so we have a nice variety to look at. So I'm going to jump down here to number 7. So notice it is changing. We're finding sides and angles now. So kind of an intermingled review that may affect how I set this relationship up. So I'm not going to tell you whether we're going to use inverses or not. We're just going to let the equation guide us. So we're finding x, rounding to the nearest tenth as needed. So again, doesn't matter where your variable's at, setting up the equation, you need to use your angle measurement. That should be your focal point. Because with respect to that angle, it's going to change whether we have opposite or adjacent and vice versa. So in this case, with respect to that angle, what would the 11 be?
Opposite.
It's the opposite leg. Okay. What about x?
Adjust.
That's on the adjacent leg. Okay. Opposite and adjacent, I should be thinking
Tangent.
tangent. So I'm going to set up what I have. So the tangent of the angle, which we actually have this time, so tangent of 39 degrees equals the opposite leg 11 over the adjacent leg x. Now, those of you who practiced over the weekend from the assignment on Thursday, you might recognize, this is that one where the variable ends up in the denominator, and I have to do kind of a switcheroo of sorts. It's not really a technical term, but that's going to be kind of what it feels like. I want to first get that x out of that denominator. And to do that, I'm going to multiply both sides by x. That knocks it out of the denominator on the right-hand side, which leaves me with x times the tangent of 39 degrees equals 11. So I don't have any fractions now. Hopefully I feel a little bit more comfortable, but my x is still not by itself. It's still right now, it's right next to tangent of 39 degrees. Now, at first I think, ew, gross, how do I move that? But then I remind myself, tangent of 39 degrees is just a value like any other. Our calculator would give us that value. But like any value, Misty, I think I heard you say it, you should divide both sides.
By 11.
Oh, nope,
No.
by the tangent of 39 degrees, because I want the x by itself.
Oh.
So on the left-hand side, it looks like a mess, but tangent of 39 degrees divided by the tangent of 39 degrees is just one's height, which leaves me with x. On the right-hand side now, I have 11 divided by the tangent of 39 degrees. Now, this is where you kind of have to make a decision based off of, one, your calculator, and two, your comfort level with that calculator. Because technically you could enter that entire right-hand side now into a calculator and it should give you the value you're looking for. Now, if not, you could do it in smaller chunks. You could do just the tangent of 39 degrees. It's going to give you a decimal. Sorry, 8.9.
8.9.
That's not quite what I got. Let me, I might have made a mistake though. Tangent. Not quite. So try.
I know what I did wrong.
Okay, try it again. On my calculator, I simply put in exactly as I saw. I put 11 divided by, then I press tangent 39, and then I actually close the parentheses on that tangent.
13.6.
13.6 sounds a lot nicer. That's what I have. Missy, I want to make sure you get there as well.
I forgot my 5.
Division symbol.
I need
So
the
what
11
did you, how did you push it?
So type in 11,
11
divide,
by
tangent, not inverse tangent, just regular old tangent,
tangent
39.
39.
Close that parenthesis, so use the right parenthesis.
Okay, 13.5.
13 point, I think it rounds up to 0.6.
Okay.
Now notice I'm not putting degrees on this one because x was a side length this time instead of an angle. Which is why you'll notice our process in solving it changed a little bit. But we did a handful of these on Thursday. So it's not new, it's more of review. But if you were out Thursday, then it feels very new. I'm going to jump over to number 8, just because it has a slightly different feel to it based upon how our equation sets itself up. Still using that angle as my focus point. With respect to that angle, what do we have?
Hypotenuse.
We have the hypotenuse, that's my 28. And where's that x located?
Jason.
That's the adjacent leg. So which trig function?
Cosine.
Cosine. So I'm going to set this up. Cosine of the angle. It's always cosine of the angle. So cosine of 46 degrees equals the ratio adjacent over hypotenuse. So I've got x over 28. So I want the x by itself. This one's going to be a little bit easier because all I need to do here technically is multiply both sides by 28. And if you guys will, actually, I'll be a little bit more detailed on this one. I'll take a shortcut later. So I get 28 times the cosine of 46 degrees equals x. But for my purpose, I'm going to flip it around and put x first. So x equals 28 times the cosine of 46 degrees. which I happen to know my calculator can take over here, so long as I enter it in exactly as I see it. So 28 times the cosine of 46.
19.5.
That's what I got. Okay. 19.5. Good. So depending, I will say, depending on where the x is at, if I look at these two side by side, it really kind of boils down to the difference of, am I going to have a division thrown in there, or am I going to have a multiplication thrown in there? If the x is at the bottom, it's going to turn out to be division. The x is on top of my ratio, it turns out to be multiplication. Now, still set up the rest of the equation so you know what goes where. But that's kind of a simple oversimplification of what's happening here. These next two, I'm going to skip number 9 because it's just like the one above it. Very, very, very similar to it. I'm going to give you the answer, though, in case you wanted to try it out. Oops. If you tried this one, you should get x equals 6.5. I'm actually going to skip number 10 as well, because it's similar to 8. It's not exact, but similar. If you do try this one out, you should get that x equals 12.6. Seven and 8 was really the two main possible ways that it could take form. Now, obviously, sine, cosine, tangent, those could be interchangeable depending on which sides of your triangle you have. But in terms of the steps beyond that, either you're going to have a division at the end or a multiplication. I actually want to jump ahead to I want to jump ahead to 15 and 16 because they're a nice combo of both skills that we've now acquired. So with that being said, I'm going to give you the answers for 11 through 14 if you want to try those extra practice. That way you can kind of check yourself. Remember though, it could be an inverse, it could not be an inverse. Set up your equations. What you should get on number 11, x should equal 50.5 degrees. You should get 17.8 degrees. $13, 30.6 degrees. And 14 is 31.8 degrees. So I'm feeling generous. I will allude to the fact that all 4 of these will require you to use the inverse of one of the trig functions. The way I can know, the way I can tell right off the bat is where the x is located. You're actually looking for the angle measurement for these, which means your x is going to land inside your trig function. You're going to have to take its inverse to get it away. But like I said, I want to try to look at numbers 15 and 16 because, well, for one, Misty asked me a question earlier, and this looks kind of in the same realm as to what her question was earlier for me. And it's a nice hybrid version of both what we did on Thursday and what we introduced today. So I'm going to take a look at this first diagram here. it is asking me to find side DE. So I know it's kind of tacky, but I'm going to highlight it just so it kind of stands out for me. I'm looking for this little side over here. And if I take a look at what I have, let's see. Well, where DE is currently located in this bottom right triangle, I have an angle measurement, but I don't know any of the sides of that bottom right triangle. So unfortunately, I don't have enough information yet to just jump right into that side. So I take a step back and I'm like, okay, I have a second right triangle that's sitting here on top. And with respect to that right triangle, I'm going to vary my colors here a little bit. I have this side, which should be enough information to help me either find CD or FD. Now, between the two, which one would be more useful if I think as to where I'm trying to work towards?
CD.
Ooh, well, here's the problem with that. It would give me this side, but then this side, does CD have anything to do with this bottom right
No.
triangle?
Be better off with FD.
FD would be certainly helpful because not only does it tell me more about the top right triangle, it finally gives me a side of that bottom one, which is really where I'm trying to work towards. I need to know something more about that bottom one. So here's what I'm going to do. So we're not, writing a bunch of letters more than we have to. I'm going to label side FD to be X. Now, with respect to the 61-degree angle, what sides of triangle CDF do I have? Here, just look with respect to this angle right here. I have X and I have the 24. What would the 24 be?
Adjacent?
That would be the adjacent leg. And the X would be the opposite. I saw Tiara mouth it on the video. CD would have been the hypotenuse. I don't know it, and it's not really going to benefit me in this case to know it. Could I find it? Absolutely. But it'll just be extra work that I don't necessarily need. So working towards finding side FD, which I have labeled with just the variable X. I have the opposite and the adjacent. Which trig function am I going to use? Tangent. So I'm going to have tangent of my angle, which is 61 degrees. It's going to equal the ratio opposite over adjacent. So in this case, X over 24. So going through to solve this, I'm going to multiply 24 on both sides. As I mentioned earlier, I'm going to be kind of sneaky. I'm going to go ahead and flip it as well simultaneously to say X equals 24 times the tangent of 61 degrees, which with the help of my calculator, oops, 43.3. Okay. Now, I'm not done because what I just found was side FD. Right? I'm looking for side DE in the bottom right triangle. So I'm going to say, okay, I now know more than I did before. Coming down to this 19-degree angle, with this as my focal point here, I'm going to change colors. If I'm looking for side DE, which I'm going to label with a Y, I've already used the variable X. I don't want to mix up my labels here. What parts of this triangle do I have? with respect to that 19-degree angle?
And Jason,
The adjacent, which is
43.3.
the 43.3, which is my X, so this now becomes my adjacent. It was the opposite up above, but now it's gonna behave as my adjacent. And the Y that I'm looking for
Is the opposite.
is the opposite leg. So which trig function am I gonna use here?
Tangent.
Tangent again. But we need to watch where this drops here. So let's see, I'm gonna have tangent of my angle, which is 19 degrees, equals the ratio opposite over adjacent. So Y over 43.3. I'm going to go into solving mode here, multiply both sides by 43.3. That knocks it off of the right-hand side. I'm going to do a kind of a double step here. I'm going to write the variable first. So Y equals 43.3 times the tangent of 19 degrees, which with the help of my calculator, I should be able to find.
14.9.
14.9. Now, to bring it full circle, OCD kick in here. Technically, Y was representing something specific. It was representing side DE. So I'm going to say DE equals 14.9. So there's that one. So it was 2 steps. The triangle where the side that we were looking for was located, we knew nothing about it other than just an angle. So our approach was, if I could find at least one more side, we'd be in business. So we looked at the other right triangle on top, said, okay, well, they share this side, so if I can find it, I can use it later. So we went for it. How we do on time? 5 minutes. Wait. Okay. I'll try this next one here. So I'm looking for the measure of angle W. Angle W has nothing there, so I'm going to label that with my X to say X degrees. That's what I'm looking for. Now, let's see. With respect to that angle, do I know at least 2 sides of that triangle in which it belongs? So X, WXZ. Don't think we do we?
No, only one.
So what would happen is if I said, oh, I'll just put a variable here, can't solve one equation with 2 variables in it. It's going to create a headache. So I only know this side here, which with respect to that angle is what? The adjacent leg?
Yes.
It would sure be handy if I knew something else. Well, I think the hypotenuse is out because it's not tied to anything else. Gaining that information wouldn't help me. But if I look at the opposite leg, if I was looking for that piece, that might help me get a little further. So this is going to seem a little bit crowded here for just a moment, but I'm going to label that side Y. And with respect to my large right-hand triangle here on the left, that is my opposite leg. Now, here's the problem, though. I need to jump over to this triangle to be able to figure out what that measurement is. So we're in luck here. We have an angle. With respect to that angle, what do we have? We have a leg, that 15. Is that opposite or adjacent?
Opposites.
Opposite. So notice the slight color change here, just so we don't accidentally mix our values together. And I'm looking for y, which is actually what in this second right-hand triangle?
90-degree angle.
It's across from the 90-degree angle, which means it's the
Adjacent.
hypotenuse.
Apartment.
Yep. So y right now is the hypotenuse in this smaller right triangle. So with respect to that 25-degree angle, I have the opposite. I'm looking for the hypotenuse. Which trig function would I want to use here? SOHCAHTOA, looking for the OH, the S. Sine? Yeah, we're going to use the sine here. So setting it up, I'm going to take the sine of my angle, which is 25 degrees. And that's going to equal the ratio of the opposite, which is 15, over the hypotenuse, which is where my y is currently located. So unfortunately, this is one of those ones where the variable is stuck in the denominator. So this is where I got to get a little bit fancy here by first multiplying both sides by that variable. Gives me y times sine of 25 degrees equals 15. And then to fully get that y by itself, I need to divide both sides by the sine of 25 degrees. So I have y equals 15 divided by the sine of 25 degrees. Now, while you guys are reaching for your calculator, I'm going to fix my little guideline here. For this one, what does y equal?
35.5.
95.5?
35.5.
35.5. Now, remember, that's not actually the piece we're looking for. That is just a means to get us to where we're going. So if you needed some labels or context, that would be side XZ. But that's not what I'm looking for. I'm trying to find the measure of angle W, which I have denoted with the variable X degrees. So I'm going to slide over here to my second one now. Using the angle that I'm looking for as my new focal point, we've already kind of, well, at least I did, I already labeled the pieces that I had and the piece that I need. I have the opposite now. We already knew the adjacent leg. Which trig function am I going to use here?
Tangent.
Tangent. So the tangent of X degrees equals the opposite leg, which we calculated to be 35.5, over the adjacent leg, which was given to us as 22. We can then run through this process to calculate. So first thing I notice, X this time is trapped inside the tangent. I need that tangent to go away. So I'm going to use the inverse tangent, which we introduced today, to make that happen for me. Whatever I do to one side, I also have to do to the other. So I'm also going to have the inverse tangent of 35.5 over 22. On the left, inverse tangent and tangent eliminate each other, leaving me with X equals the inverse tangent of 35.5 over 22. So I go for my calculator here.
$58.2.
58.2. So that's 58.2 degrees which I need to remember back in the context of my problem, that was the measure of angle W equaled my X, which equals 58.2 degrees. So again, another two-parter there that you have to start further away than you want to get a necessary piece of information to find the value you need. So there's those two rather involved problems. Again, notice the two sets of work there that it kind of required us to set up. Now, last two there, again, if you want to give them a shot, you're more than welcome to. I want to make sure we get to the back side and get or the last page, both sides. We're going to cherry pick a couple examples there. But if you try number 17 and number 18, number 17, you should get 23.2 feet. I'm not going to put a variable there. The variable that you label is going to be based upon your own preference. And then 18 should be 33.1 degrees. Yeah, if you want to give those a shot. If I was going through those, I would first sketch a diagram to then be able to see what trig functions I need to set up there. But we're going to do plenty of that here on the last page when we introduce two unique types of angles and then figure out how we can use those angles to be able to find different measurements. So again, we're not going to do every single one of these. If we can, I'm going to try to squeeze in two of each. If not, we're definitely going to do at least one of each. First page or first side here is all about what's known as an angle of elevation. So if you take a look here, there's a neat little diagram of a boy looking up at the top of a lighthouse. So it says, when looking up to an object, the angle of elevation is formed by the observer's line of sight. So if you were to draw a line from your eyes up to what you're looking at, and a horizontal line, which is usually the level of your eyes with respect to the ground, you create an angle of elevation. So notice this boy is looking at the top of this lighthouse, which is his line of sight. If you were to draw a horizontal line from his eye level, you then create, in a way, a right triangle, and primarily you create what's known as an angle of elevation. Now, that key word is going to help us set up, or we're going to sketch a diagram, then set up an equation to help us find a missing part. Now, we have to be careful though, because sometimes it's kind of sneaky. This first one is a good example of that. So, number one here says Casey sights the top of an 84-foot tall lighthouse at an angle of elevation of 58 degrees. If Casey is 6 feet tall, how far is he standing from the base of the lighthouse? Now, a quick side note, I totally geek out on these types of problems because, hypothetically, with a tool known as a sextant, which you can actually make out of a weight, some string, and a toilet paper roll, and a protractor, I should say, you can measure an angle of elevation. This is what the sailors back before GPS was a thing used to do. Measure your angle of elevation and be able to determine the distance away from something or the height of something using your trig ratios. It's a really cool process. If you're like, I don't really care. Okay, that's fine too. But it allows us to kind of set up a really interesting set of information. So I'm going to sketch this here. Again, try not to laugh too hard. Here's Casey. Ooh, Casey's really tall and skinny. Here's Casey. Casey's looking at a lighthouse. So I'm going to be extra bougie here real quick. Or if it's gonna let me do it. Nope, didn't like that. There's my kind of sad looking lighthouse. Oops, it's not level with Casey. We're assuming that they're standing on the same level. Again, I won't grade you on your artistic ability because obviously I have done. But what we have here, the information we're given is we know for a fact that the height of this lighthouse is 84 feet. We have KC, which we know is 6 feet. So this is by no means to scale because that's not even close. Then we have Casey is looking at the lighthouse, creating an angle of elevation. So we're going to draw to the lighthouse with respect to the tippy top of the lighthouse and then back down again. It said the angle of elevation, dang it, that's formed is 58 degrees. We want to figure out how far away he is. Is that correct? So X is going to be right there. Now, the problem, though, is if you're looking at this right triangle in here that's kind of overlaid the situation, I have my angle of focus that I'm going to use. It's that angle of elevation that was described to me. I'm looking for the adjacent leg. Unfortunately, I don't have the hypotenuse or this measurement right here. But do I have enough information to figure it out? This takes a little bit of imagination and creativity. I'm going to scoot this out just a little bit because I know how tall the tower is, or the lighthouse. Is that correct?
Yeah.
So if I look at where Casey is at, though, he is already taking up how much of that?
6 feet.
He's taking up 6 feet of that 84 feet, which means how much of that is left for that opposite side of the triangle? How would you figure that out?
Drop it.
Subtract 6 from 84, which is, I think, 78.
Yes.
Which is the side of the triangle I'm looking for. Now this diagram's getting real busy, but if I peel away what I need now, I already said that we're looking for the adjacent leg. I now have enough information that allowed us to figure out the opposite leg. Which trig ratio am I going to use? Tangent. So according to the information in the diagram that I've sketched out, I'm going to have the tangent of 58 degrees equals the opposite, which is the 78, over the adjacent, which is what we're looking for, which is the X. And then we're going to go into solve, solve, solve. Unfortunately, this lands my X in the bottom, so I need to do that quick switcheroo there. Multiply both sides by X. And then to get that X completely by itself, I'm going to divide both sides by the tangent of 58 degrees. And I get that X equals 78 divided by the tangent of 58 degrees. With the help of the calculator, what does that give me?
Put 7.
48.7. Now remember, this is a story attached to it. It's not degrees. Everything else is measured in feet, so we got to stay relative to that. So we can say then that Casey here is 48.7 feet from the lighthouse. I actually want to jump to what time is it? Oh my God. Never enough time. Let's take a look at number 2 real quick, and then I'll give you the answers for the other ones, and then we'll do angles of depression on the back. Number 2 says the angle of elevation from a kicker's foot on the football field to the top of the goalpost bars is 17 degrees. If he is standing 131 feet from the base of the goalpost, how tall is the goalpost? Well, let's see here. Let's put, what's his name? The kicker, he doesn't even have a name. That's sad. Put our kicker right here. Oh gosh. It's measuring from, with respect to his foot to the top of the football goal. So we're gonna, oh gosh, I'm gonna embarrass myself here real quick. So the top of the football goal there, it told us that the angle of elevation is 17 degrees. And it also told us he is standing 131 feet from the goalpost. We want to know how tall the goalpost is, which is just this side right here. A little bit easier diagram to sketch out. Still using the angle as our focal point. With respect to that angle, what sides do we have?
Hypotenuse.
Oop, careful. Hypotenuse is right here.
Okay.
Where would the X be with respect to our 17-degree angle?
Opposite.
It is opposite, which must mean the 131 is adjacent. So which one uses opposite and adjacent? Tangent. So tangent of 17 degrees equals opposite over adjacent. So X over 131 get X by itself. I'm going to multiply both sides by 131. Take a little shortcut here and flip it around for myself as well. So X equals 131 times the tangent of 17 degrees.
$40.05.
Careful, I think what comes after the 0, depending on who you talk to, I usually 5 and up, I round up.
40.1.
40.1. And because we're measuring the height and everything else was measured in feet in terms of lengths, that's 40.1 feet tall. Now, if you want to try the last 2 on this page, I will give you the answers real quick. Number 3 should be 12.5 feet. Number 4 should be 72.6 degrees. Again, you would start by sketching a diagram, figuring out with respect to the angle you have or are looking for, what sides of the right triangle you have, and then set up your equation. I want to make sure we had time to look at least briefly at angle of depression, which is basically the opposite of angle of elevation. Instead of looking up to an object, you are now looking down at an object. So an example here is a lifeguard looking down at a swimmer. So it's formed with the line of sight, so you looking down at something, and a horizontal line out from your eye level gives you an angle of depression. Now, here's a neat little tidbit of information. The angle of depression is congruent to the angle of elevation because they are alternate interior angles. Oof, that's ugly. Why did it do that? Now, when it's referring to the angle of elevation, it is referring to the person at the other end. So the lifeguard is forming an angle of depression down, looking at the swimmer. We're using a horizontal line out from his line of sight. But if we think about it in terms of the swimmer being horizontal with the ground as well, and he looks up, we do have alternate interior angles, which means this angle is congruent to the angle of depression. Alternate interior. So if you are the lifeguard looking down versus the swimmer looking up, the person looking down has an angle of depression, which is the same as the person looking up's angle of elevation. Little bonus tidbit of information there. Now, let me see here. For the sake of time, so you don't hate me completely, I'm actually going to skip the first three. Thanks. Hold on. I might have lied to you. I'm just going to do number 6. So number 5, if you were to try this one, it would be 24.6 feet. Number 6, I like this one because theoretically, if you were a pilot and your instruments were to go down, in theory, you could do these number crunches on the fly. That is assuming you have access to at least a basic calculator. But anyways, a pilot in a helicopter spots a landing pad below. The angle of depression is 73 degrees and the horizontal distance to the pad is 1,200 feet. What is the altitude of the helicopter? Well, I'm going to sketch this out here real quick. Don't make fun. So here's my cutesy little helicopter. And he is looking down at a landing pad, which we'll say over here. It says that a hotspot lane angle of depression, so creating a horizontal from where he's at. He is looking down at this landing pad with an angle of depression of 73 degrees. We know that his horizontal distance is 1,200 feet. So I'm actually going to, sketch this down to here. Of course, it didn't line up. So the distance, horizontal distance is 1,200 feet. we want to know its altitude, which is its vertical height. Now, something weird happened here. The angle I have isn't in the triangle that I've drawn. But I don't panic because a horizontal line, which is at the helicopter, and the horizontal line that's the ground should be parallel, which if you refer to the statement up above, these would then be alternate interior angles, which means this is 73 degrees as well. It's just an angle of elevation. So using that angle as my focal point, what do I have? What sides of the triangle do I have, or am I looking for?
That's adjusting.
So I have, yep, I have the adjacent, and I'm looking for the opposite. Which means I'm going to use which trig function?
And
Tangent. So I'm going to say tangent of my angle, which is 73 degrees, equals its ratio opposite over adjacent. So x over 1,200. And then I'm going to get that x by itself. So first thing I'm going to do there is multiply both sides by 1,200. And I'm going to go ahead and flip it around so my x is on the left. I get that x is equal to 1,200 times the tangent of 73 degrees. So what is the altitude of that helicopter? $3,925 feet. Now, a lot of you are thinking, well, there's tools for that. Of course, it cuts out. So minor technical difficulty, but our final answer when we're done should be 3,925 feet is the altitude of the helicopter. Now, yes, most flying aircraft have what's known as an altimeter, which tells you the altitude. I don't actually know how they work. I'm sure that there's math involved, maybe this math, in fact. But yeah, if your instruments were to go out and you needed to crunch those numbers, this happens. All right. So for the sake of, if you wanted to try the remaining two, number 7, the answer is 193.2 feet. And number 8 is 141.1 feet. Now, the hardest part about these, I would argue, is maybe setting up the diagram based off of how you interpret the information. But once you can find that right triangle hidden in that scenario, hopefully based off of the previous experiences and the previous practice problems, once you see your right triangle, you should be able to pick out whether it's the opposite leg, adjacent leg, hypotenuse, and go from there.